Okay. Hello, everyone. Here I'm going to represent to you my latest study on fossil fuel-based energy storage technologies. This report has been released recently. And this is the outline of my presentation. I will begin with the discussion of the need and opportunity for energy storage, followed by a brief review of the available and emerging grid-scale energy storage technologies. I will then discuss the feasibility of integrating a storage system into a coal-fired power plant and the techno-economic analysis and comparisons of different integration solutions. Finally, the key findings of the study. Today, an energy system has to adopt increasingly higher share of intermittent renewable power. This introduces variability and uncertainty to the system, making it more volatile and therefore challenging to balance the demand and supply of electricity. This challenge is clearly illustrated by the Californian dark chart shown on the left, in which you can see how the morning and the evening ramps have been exacerbated by the increase in solar and wind power. For example, the total installed solar and wind capacity in California increased from 6.2 gigawatts in 2012 to nearly 16 gigawatts in 2016. As a consequence, the maximum ramp needed increased from around 3 gigawatts to 11 gigawatts in the same period. Energy storage system can provide a host of services to support the grid and address some of the challenges brought up by high penetration of variable renewable power. Energy storage enables maximal integration of renewable energy by storing excess electricity and inject it back to the system when needed. It also significantly reduces the need for power plants to provide fossil power plant to provide flexibility. It has been projected that the grid storage market could hit 112 billion US dollars in annual revenue by 2035, with 223 gigawatts hour of storage systems installed. Various energy storage systems are commercially available and are in operation around the world. Several new technologies are emerging into the market and more are under development. According to the form in which the energy is stored, the technologies can be broadly divided into 5 categories. Chemical storage system convert energy to chemical and the electric energy to chemical energy via production of a chemical such as hydrogen and syngas, usually based on electrolysis. The chemical can later be used as a fuel to support the thermal load for power generation or for transport. Mechanical storage systems store energy in the form of either potential or kinetic energy, and they include pumped hydro, compressed air, and the flywheel storage systems. Electrical energy storage store electricity directly in the form of electric current or electric charges with a potential difference. Superconducting magnetic energy storage, or SMES, and the supercapacitors are the 2 forms of commercial electrical energy storage systems. Thermal energy storage, or TES, heat or cool a storage medium such as water, rocks, and the molten salts to store thermal energy. For electricity storage purpose, high temperature TES is used. The stored heat is converted back to electricity using a conventional steam turbine. Electrochemical energy storage involves storing electricity in chemical form. It includes different types of batteries and is one of the most traditional energy storage technologies. Commercially available batteries include sodium sulfur, lead acid, and lithium-ion batteries. Pumped hydro is a well-established technology and can provide high power and energy capacity and long-duration storage. It can be used for time-shifting, reserve generation, and is suited for long-term storage, such as seasonal. Flywheels, SMES, and supercapacitors are commercially available, and they are high-power, short-duration storage systems, and can be used for frequency regulation, voltage stability, and power quality management. Compressed air, TES, and batteries can have power and energy capacity of multi-megawatts and megawatt-hours, and the discharge durations of up to several hours. They can provide a range of ancillary services and can be used to smooth out intermittent renewable power generation, thus balancing and stabilizing the grid. Chemical storage can provide long-term storage and flexibility with the end use of the chemical produced. Energy storage can operate as a standalone system or be co-located with power generation facilities. For coal power plants, there is an alternative to integrate a storage system with generating units to obtain some operational advantages, such as enhanced flexibility. Integration with energy storage could eliminate the need for excessive flexible operation of coal power plants, enabling them to operate at optimal output and efficiency with reduced environmental impacts, leading to several benefits as listed here. TES is well suited to be integrated into the water steam cycle of a coal power plant. It's proven that it is technically feasible to integrate TES into a coal power plant. Analysis showed that the integrated coal TES plant has enhanced flexibility, fast dynamic responses to load demand change, and performed better than a coal power plant in grid frequency services. Conceptual designs have been developed, but large-scale field tests are needed. Existing coal power plants retrofitted with batteries are already in operation in China, and dozens of hybrid battery renewables, battery gas turbines, battery and natural gas combined cycle power plants are operational as well. The successful integration depends on the development of interfaces connecting the coal power plant and the battery pack with a control system that brings the two systems together to work harmoniously. No modifications to the power generation process are needed. In the hybrid battery coal plant, the battery pack works as a supplement to the operation of generating units, enhancing the plant flexibility and overall performance, as well as offering enhanced ancillary services such as frequency regulation, spinning reserve without fuel burn, higher peak power output, instant power to grid, and a faster startup. Similar to hybrid coal power battery plant, effective connection of coal power generating units with water electrolyzers using a dynamic control system is key to the successful integration. In an electrolyzer coal power hybrid plant, the electrolyzer do not necessarily inject the stored energy back to the grid, nor do they provide any ancillary services like batteries. The electrolyzer enhances the flexible operation of coal power plants by absorbing the surplus electricity whenever it is generated. The major advantages of hydrogen for energy storage are the length of storage time that is possible and the bulk energy storage capacity. Techno-economic analysis show that molten salt TES is the choice of technology for integration, especially for retrofit projects, due to its lower cost and a higher maturity level than the competing TES technologies. Lithium-ion batteries have advantages over competing battery technologies of commercial acceptance, high energy and power capacity, higher efficiency and availability, and a longer cycle and calendar life, although they have high cost. Polymer electrolyte membranes, or PEM, have advantages over alkaline electrolyzers of better overall performance and compact design, but they are more expensive. In general, integration of storage system into a coal power plant are expensive. Retrofitting a coal power plant with TES is cheaper than batteries and water electrolyzers. Hybridizing lithium battery and the coal plant require a capital investment substantially higher than that of coal power TES or coal power electrolyzer integration. Lithium batteries and the water electrolyzers also have a higher reinvestment cost due to the need to replace cells that degrade. Therefore, R&D to improve the technologies and reduce the costs by, for example, increasing cycle life, avoiding the use of expensive and critical materials, improved engineering design, and potentially make breakthroughs in the emerging technologies, as well as techno-economic assessment are needed. So the key findings from these studies are: technically, it is feasible to integrate thermal energy storage, batteries, and chemical energy storage systems with coal power plants. Each integration solution provides flexibility in different ways. Integration of coal power plants and the storage system can potentially enhance the flexibility of the assets and the overall system efficiency and improve plant economics. Pairing storage system with coal power plants has high cost and more R&D and techno-economic assessment are needed. That's the end of my presentation, and thanks for listening.